What I'm going to talk about now is has to do with both chemistry and physics, heat transfer mostly. So chemistry and physics. And I will base my talk on a book by An Introduction to Fire Dynamics by Professor Dougal Drysdale in Edinburgh. So we use this book a lot to teach, or material from this book to teach our students about ignition and flame spread. This is quite a big area, and so I have decided to boil this down to a 3/4 of an hour or a 1 hour talk about the things I think are important. And what I think is important to do is what we will do is we will start by talking about two types of flames. There's pre-mixed flames and diffusion flames. According to God Almighty, there are only these two types of flames. No other flames. It's either this or that, and there's no magic in between. And we will talk about pre-mixed flames and flammability limits and explosions and things like that, which happen in the gas phase. Then I will talk about what happens to liquids, and then I will talk about what happens to solids. And then we will go a bit more into solids. We'll talk about thermally thin, thermally thick solids. The solids are a bit more difficult than gas and liquids. Gas is easy. Liquids are a bit tricky. Solids are difficult. And then I will talk about smouldering combustion. Because God also said there are only two types of combustion in the fire sense. There's flaming combustion, where you have flame, or smouldering combustion. I'll talk a little bit about smouldering combustion, and then I will say a few words about enclosure fires, how we apply this in enclosure fires. So that's the structure of my lecture, and let's start. So there are just two modes of combustion when it comes to fire safety. There's either you have a flaming combustion, which is most often what we have in the fire service, or you have smouldering combustion, like a cigarette. That can also happen, of course, in our business. And flaming combustion, you have some gaseous fuel plus air or oxygen, which produces flame, products, and heat. And you can have just two types of flames, just these two types. Either you have a pre-mixed flame, or you have a diffusion flame. We most often talk about diffusion flames. That's an ordinary fire, gasoline burning, or chair burning, or something like that. That's a diffusion flame. I'll talk about what it is, what it is. But the pre-mixed flame is where we have the fuel and the air is already mixed before we ignite it. Like in the gas stove at home, the gas comes up, it's already mixed, and we get a blue, very, very hot, very effective combustion. There's no soot, there's not nearly any soot. It's very effective combustion. The flame is blue or nearly see-through. That's a pre-mixed flame. And the gas and the air are mixed before we ignite it. The other situation is a diffusion flame, and we call it diffusion flame because the gas comes out, or the table is burning or something like that, and the gas, the fuel, is not mixed with oxygen or air before we ignite it. The gas comes out and then mixes with the oxygen and burns where it is mixed. And it's called a diffusion flame because it's called the process of diffusion, when the air is sucked in to the combustion zone. It's called called diffusion, by the process of diffusion. Therefore, it's called a diffusion flame. So there's a premixed flame. The gas that's coming out here is already, say, 10% gas, 90% air, or some kind of oxygen or something, usually mixed with air. Sometimes we mix oxygen and gas, like when we're cutting with a welding apparatus or some cutting apparatus, right? But more often we mix it with just air. So that's maybe 10% gas, 90% air, something like that. Comes out like this. Extremely effective, very, very hot. Very little soot. And here's a diffusion flame. So the gas, the fuel gas is coming up here, and it gets oxygen from the side. It gets air from the side and mixes there and burns. Mixes and burns. So that's a diffusion flame, that's a premixed flame. And in premixed flames, the fuel vapor and the air are mixed intimately before ignition. And when we talk about this kind of combustion, we talk about flammability limits. There's something called flammability limits that apply. That does not apply for diffusion flames. And that's my point here. Because in the diffusion flame, there's 100% gas there. There isn't any limit at all. There aren't any flammability limits when we talk about diffusion flames. Therefore, when people talk about lean flashover or rich flashover, meaning that the mixture is thin or the mixture is very thick or something like that, that's we're talking about a diffusion flame, and therefore it's not quite right to talk about lean and rich flashover or something like that, because it's in essence a diffusion flame that we're talking about. So let's talk about premixed flames a little bit. Let's talk about these things called flammability limits. Or let's talk about so flammability limits do not apply for the diffusion flame. So this is a diffusion flame, a typical diffusion flame, where the gas, the combustion, of course, is in gas phase. So there's some gas coming out of this solid, and the gas mixes with oxygen somewhere just above the surface and burns and combusts just above the surface. The flame is always a gas phase thing. It's not really the solid that's burning. It's the gas just above the solid. And heat is being transferred in and out and so and so. And the air is entrained from outside. And we're going to talk about liquids. The fuel vapor from the sort of boils, and we get a liquid. If this is a liquid, the fuel vapor comes up here. And for a solid, the fuel vapor comes from a chemical decomposition of some sort. Call it pyrolysis. Pyrolysis. It's a process when a solid turns into gas. And so for liquids, it's simple. The liquid simply evaporates and becomes vapor or gas and burns. For solid, there are quite a few ways to get it into gas phase. You can first, sometimes it goes into liquid and then evaporates into gas phase. Sometimes it goes through something called sublimation, when it just breaks down and goes into gas phase. Sometimes there's chemical decomposition and vaporization and then gas phase. And it's in many cases, not all of the solid will burn, and some of it will combust, some of it will turn into char, but some of it turns into gas and burns and produces heat. I'm going to say a few words about premixed flames. and flammability limits. If you've already mixed the gas and the air, then you will get something called the lower flammability limit and the upper flammability limit. For methane, for example, if you have a mixture of methane, which is 4.9% methane, and 95.1% air, you will not be able to ignite it under ordinary circumstances. It's too little methane. But as soon as you get up to 5% methane, little spark, and it'll ignite. Also, if you have more than 15% methane, more than 15% in this air, you will not be able to ignite it either. Methane will have to be somewhere between 5 and 15% mixture with air if you want to ignite it. The optimal is somewhere around 10%. That's when all of the methane will turn into energy and then H2O and CO2. So it's called the stoichiometric concentration. It's a kind of the optimal mixture where you get most explosive power. And so there are different flammability limits for different gases. This is the way that we talk about ignition. When we're describing gases, we say these are the ignition characteristics of these gases really. There are some complications, of course. You have to apply a certain minimum ignition energy. This is millijoules. This is very low, actually, and they have sort of different minimum ignition energies here. Usually it's just enough to turn on a light switch. The little spark that comes there is more than enough to ignite a mixture. Also, there's a material property that we call autoignition temperature. And this is the temperature when we have a stoichiometric mixture of this, and we heat the gas up. At some point, it becomes so hot, and the molecules move so very fast and vibrate so very much that once we heat it up over 600 degrees, they just ignite without any spark. We don't need it. We don't need any spark. They just ignite and explode. So, so when we talk about gases, we often talk about these kinds of characteristics. And we know if we have a good stoichiometric mixture, we will get an explosion. And the severity of the explosion has very much also not just to do with what the mixture is and things like that, but what the structure is like. So if we have a very solid concrete building and concrete roof, the explosion will be very devastated because the pressure will have to get out and everything is going to collapse. But if we have, say, concrete walls and floor and a very, very light roof, then we will have the explosion, the roof will blow off, but the walls might actually stand. So it depends on the structure. This, for example, here's it was a gas explosion in a kitchen in this apartment here. The whole corner of the structure just collapsed. We can also, just to mention it, if we have dust particles, then these can also ignite and cause an explosion. We can have a dust explosion also. So that was my very quick summary of ignition and premixed gases. Flammability limits, basically, that's what we talk about there. Now we'll talk about liquids. So what's the relevance of premix burning to fire? And, it has to do with ignition of liquids and solids, and we're going to talk about that. Now, the way we measure sort of ignition propensity of some kind of a liquid, we measure it in it's called flash point or fire point, and we measure it in a cup. I'm going to show you a picture of this. So this is actually, we take a cup like this, we pour some petrol or something into the cup, or not petrol, it's not a good example, say ethanol or something, and we heat it up, and then we put a little spark just above the surface in the gas phase, put a little spark, it doesn't ignite, then we heat it up a little bit more, try to ignite it, we heat it up more, and heat it up more, and finally we come to a temperature which we call flash point. It's a certain temperature at which, if you heat the liquid up to this temperature, then it will ignite the vapors. And it's called a flash point when you ignite the vapors and it doesn't continue burning. If we heat it up a little bit more, we ignite the vapors and it continues burning. So it's flash point when it flashes like this. We heat it up a little bit more, and then we get to what's called the fire point. That's when it ignites and it continues to burn. So we use these two words to describe liquids, or describe the ignition propensity of liquids. So we say, oh, this liquid has a flash point of 45 degrees or 50 degrees, and flash point of 60 or something. I'm going to show a bit more about this. So the flash point is when it flashes, the fire point is when it's continued burning. We measure the flash point in a standardized, there's a standardized method to measure that. It's called the closed cup apparatus. And the fire point, we measure that in the so-called open cup apparatus. So this is a closed cup apparatus. We pour the N-decane, for example, is a liquid which it's a part of petrol. You actually have to, you pour it in here, you actually have to heat this liquid up to 46 degrees Celsius before the spark will ignite it. And so we say N-decane has a flash point of 46. And therefore, we say, it's not a very dangerous liquid. What's a dangerous liquid? I would say a liquid that will ignite at room temperature or lower. That's dangerous. Because if we have a liquid with room temperature and I just need a little spark, it'll ignite, then that's a dangerous liquid, and we classify it as a dangerous liquid. But if the ignition temperature is more than that, you have to actually heat it up to get it to ignite, then it's somewhat less dangerous. And so this is the way that we classify liquids. And N-decane, for example, it has a flash point in the closed cup of 46. If we heat it a little bit more, if we put it in an open cup, and we heat it a little bit more, that we need to heat it a little bit more if we have it in an open cup. And it'll flash, and then we heat it just a bit more, and it will actually continue to burn with a sustained burning, with the fire point. There is a difference in the temperature, because now let's say that I heat this up to 46 degrees, and then I will collect a lot of unburnt gases here, and so therefore I only need to heat it to 46, and then I put a little spark in there and it'll flash. Okay? If I have it an open cup, then the concentration of gases, it'll actually rise and just go away. So therefore I actually have to heat it up a little bit more here to get it to flash. Why do we have open cup, closed cup, and so and so? It's probably historical reasons. When very many years ago, when they decided to classify liquids, to say this is a dangerous liquid, this is an okay liquid, they had to find out a method of doing it, and they found these two methods, and these became the standard methods. So that's just, it's historical how it happened. Now, now let's have a look at some liquids. So the closed cup flash point, if we just look at that, the lowest temperature at which a flammable mixture will exist just above the surface. Let's have a look at a couple of. Gasoline, for example, this is an extremely dangerous liquid. You have to freeze it down, cool it down to 38 degrees, minus 38, if you're going to make sure that this gasoline doesn't ignite when you put a little spark on it. You actually have to freeze it down to minus 38. If I have this liquid, gasoline, at room temperature, it just needs a tiny little spark and it'll ignite. So this is a dangerous liquid. This endocane is not as dangerous. I would actually have to, if I have it at room temperature, I would have to heat it up a little bit before I could ignite it. And kerosene, for example, is over 37. So when I ignite a kerosene lamp, I usually have a wick or something so that I can heat it up there. So I have to heat up the liquid or the gas as it comes up to the wick. If I have a kerosene in a bowl and I want to ignite it, I will actually have to try quite a bit with my lighter. I will have to try heat it up, heat up the surface at some spot, and then it'll ignite. And so you can see that this is the way that we classify liquids. Let's have a look at some. This is from the Ignition Handbook by Babrauskas, huge thing called Ignition. It's a huge Bible of ignition, let's say. So this is actually the answer to your question earlier, is that when we look at an open cup measurement, and the vapor concentration is quite high just below here, but it decreases as we go up. The vapor concentration decreases. Therefore, we have to put the spark very close to the surface. If we put the spark up here, it's not going to ignite. But in the closed cup, it's actually reasonably mixed, and it'll ignite there. So let's see. Just a few words about the height of the ignition source above the liquid surface. So this is millimeters. So if we go 10 millimeters above the surface, we will have to actually have quite a high temperature. This is temperature. This is millimeters above the surface. And so this is endocane, for example. I just want to show what the effect the height of the ignition source has. So it won't ignite below 52 or something. But if I put the ignition source very close to the surface, I can ignite it at 53, and so and so. But if I have the ignition source above, more than 1 centimeter above, I will have to heat it a bit more. So this is called the open cup flash point, and this is the fire point. Now, here's how we classify liquids in terms of ignition. So this is UK, this is USA. I'll take Europe here. So we say that everything, liquids that ignite under the temperature of 21 degrees, they are highly flammable. They are dangerous. They're highly flammable. Liquids that ignite between here, they are flammable. And these, we usually call them combustible liquids, etc. The UK has slightly different, each country used to have slightly different. We're hoping that the European Union will take care of harmonizing this. So this is a fire because there was a guy, when a junior waiter tried to top up a flambe lamp with kerosene oil. So these things happen often when you when you have something that ignites at, say, 37. There's a flame, and this liquid is burning. There's a flame, and the liquid is nearly finished, and this waiter, and the bowl is extremely hot. And this waiter is going to pour more liquid into an extremely hot metal bowl. And it'll create, immediately when it hits the very hot bowl, it creates a gas that you don't see, and it goes up and it explodes in your face, and all the hair goes off like this. Not only that, but the whole damn building burnt down. So that's so we have a flammable and combustible liquids. They must be heated above their fire points for them to ignite. And diesel oil is often used in industry. You have to actually heat it up for it to ignite. Sometimes it's in a pump and it's already hot, and then you get pump failure and some sparks and stuff, and so you can ignite. You often in industry you have a ignition of diesel oil because the diesel oil is actually hot. But often diesel oil is a pretty decent fuel because when we use it in fire experiments, we actually have to have a gas lamp and heat up the surface. Oh, show that. Surface heating. So bulk heating or surface heating. We can bulk heating, for example, when you're making French fries, you heat up the oil in bulk. But if you're doing a fire experiment and you have your diesel oil in this pan, you have to have a gas flame, and you have to wait and wait and wait and wait until the area where you're heating the diesel oil becomes 72 degrees, and then finally it ignites and the whole surface ignites very quickly. So sometimes you have a wick to help you do that, but when you heat up this area here, say, then you will have some flow and some mixing, and when it ignites very quickly over the whole surface. So that was on diffusion flames and liquids. Let's turn to solids. Solids are more difficult. They do have flash points and fire points, but they're very difficult to measure. So now I have this solid, and I'm going to say, is this a dangerous solid or is it not a dangerous solid? And I ask myself, at what temperature does it ignite? And it turns out that most solids, or many solids, they ignite at around maybe 300, 400 degrees. So there's not very much. However, it is very different how quickly they ignite. So it's not very good to use ignition temperature to classify solids. Most of them ignite at 300 or 400 degrees. Let's talk about this a bit. The method of heating has a very great effect on this. So therefore, we do not classify solids, ignition of solids, as a function of temperature or surface temperature. We use another method, time to ignition and stuff like that. So, well, let's go through that. So, the fire properties of a combustible solid is really how easy is it to ignite this solid? How easy is it? And when I ignite it, how quickly will it spread the flame? So those are the things I want to know. Also, when I've ignited it, will it give me a lot of energy or just a little bit? And finally, what kind of toxic gases will it produce? So solids are much more complicated than gases and liquids when it comes to trying to classify them according to ignition propensity. So some of these are not really material properties. They depend on the fire scenario and the orientation of the fuel, what the fuel is it like this or like this, and so on and so on. For example, the smoke and toxic gases depends very much on the fire scenario. How much oxygen do I have? If this is burning in little oxygen, then I'm going to be producing a lot of very different toxic gases. If it's well ventilated, then there will be a different, there won't be the same toxicity, it'll be different composition. So let's talk about this a little bit. So when we talk about ignition or ignitability, we distinguish between two types of ignition. One of them is piloted ignition, which means I bring a spark or a flame or a heated surface or some energy source. I bring some energy source to the solid, often a spark, to see if the gases above the surface will ignite. That's piloted ignition. Another ignition phenomena is spontaneous ignition. That's when the solid doesn't need a spark or anything. It just suddenly, spontaneously ignites. So we'll talk about these two different ways of ignition. Start with piloted ignition. So there is a certain critical surface temperature for solids and also for combustible solids as for liquids. But it's not a very good way of measuring ignition propensity. There's also a critical heat flux of, you actually have to get a certain amount of grams per second of fuel vaporizing so that it can ignite and sustain ignition. So there will have to be a flow, it's called the critical mass flow of combustible gases so that we can actually ignite it. It's not enough that it just comes a little bit. So these can be confirmed experimentally, but they're very configuration dependent. So the piloted ignition chart is like this. We have a source of energy and exposed material, and we have sufficient flow of flammable vapors coming from this surface, and we have some pilot source, a spark or something, and then we can establish a flame at the surface. We can measure what is the surface temperature which makes sure that there is a sufficient of flammable vapors here. We can check this, and then we have to have a pilot source or a hot surface or a flame or a lighter or something. Now when we measure all kinds of different materials, these are plastic materials. This is plexiglass or PMMA, for example. Let's take that. These are some other polyurethane foams and stuff like polystyrene and things like that. These are plastics. They're quite flammable, quite dangerous solids really, or sort of flammable solids. But they all ignite at roughly similar temperature, 300, something like that. So measuring the ignition temperature at the surface of a solid doesn't really give you a good idea of whether this is a very dangerous material or not. It doesn't give you that. So we have to have some other, and we have to have these heat fluxes so that we can produce enough vapors. So we have to have an external heat source heating this solid up to get enough of the flammable vapors up. And it's about this. So this is not a good measure of whether the material is dangerous or not. So this is how we, we could measure flash point, fire point. What we're talking about is we heat the solid material up, some temperature. This is time. So we heat it up, and at some point, something will start to be released from the surface. Some kind of gas will come out of the surface. That's not enough, and it's only here at T2 where suddenly something flashes. We burn what's the gas that's there. We have to heat it up a little bit more, and then it actually starts burning by itself, and sustained burning, so it keeps burning. So this is the process. And now, if we heat it up even more, we don't have any spark or anything. We will come to a temperature at some point where the gases just above the surface will actually spontaneously ignite. But that's gaseous spontaneous ignition because the molecules are vibrating very, very much, and suddenly they'll just combust, even though we don't have a spark or a lighter or something like that. So there is also a spontaneous ignition of the gases at some point, autoignition of the gases. You have to heat it up pretty much, up to 500-600 degrees often. So the spontaneous ignition graph is like this. You have a source of energy, you have exposed material, and a flow of volatiles at high temperature. It has to be high temperature and sustainable conditions, and then finally you will have spontaneous ignition in the gas phase. So what can we do about, since we can't really say how dangerous these solids are by measuring surface temperature, how can we then measure it? What we do is we found out that we have to distinguish between either thin materials like curtains and things like that, like this material, and thick materials, that's kind of walls or particle board, or materials that are like thick, this thickness or more. Because the heat transfer thing is very different. I'll just talk about that, why we have to distinguish between thin and thick. So we have two very different testing methodologies depending on whether we have a thin material or a thick material. So there's a number called the bio number, which is a dimensionless number that's often used to tell you, is this a thick material, is this a thin material? I'm not going to go into explaining what that is, but basically it's like this. This is a thin material, and we have some heat flux coming in at it, but it cools at both sides, this thing. So there's a lot more cooling in this scenario. Whereas, and we know that time to ignition, so what we're trying to develop here is how long time do I have to heat this material before it ignites? That's a good way of checking out whether a material is dangerous or not. Time to ignition is actually often a function of the thickness. The thinner, the quicker, usually. Okay? So this is the equation. I'm not going to go into the equation. I'm just going to say we can use the transfer, the laws of heat transfer, just simple laws of heat transfer, to just calculate this with a lot of assumptions, of course. But so we calculate time to ignition, and it is the time to ignition is a function of the density of the material and the thickness of the material and the heat capacity. So if we have a very light material, something very light, it's usually very quick to ignite. If you have very heavy, it takes a long time. If it is very thick, it takes a long time. If it's very thin, it takes a short time, and so and so. So basically this is, so we say time to ignition is a function of the thickness, but it's also a function of the density of the material. Now, if we have a look at thick fuels, then we send the heat flux in here, but the heat will go into the material. So what's important here is to check how quickly will the heat go in. there will be some cooling at the surface, some re-radiation and stuff, but the main point here is how quickly will the heat disappear in. Now, if the heat disappears very quickly in, it's going to take a long time for the surface to get up to 300 or 400 degrees, which is needed for ignition. So if all the heat disappears in, if it's a bad conductor, so to speak, then it'll take a long time to ignite this material at the surface, because it takes a long time for the surface to heat up. However, if this is a very insulating material, say we have polystyrene or something, a very good insulator, the heat doesn't go in easily, but the surface heats up very quickly, and therefore time to ignition will be very short. So it's all about how quickly we heat the surface. And the quicker we heat the surface, the faster the time to ignition. And the time to ignition is a function of the thermal inertia. It's called thermal inertia. It's K rho C. So K is the conductivity of the material, rho is the density, and C is the heat capacity of the material. So these are properties that we can measure, or sort of. And yeah, it's all, you always have to make assumptions when you're measuring things. So somebody would say it's an apparent property. So the K rho C, you have to, we can measure that. As you see, the rho is here. So if you have very, very heavy materials, usually it'll take a long time to ignite. If you have very, very light materials, usually they will be quick to ignite. So this is this is the surface. This is the way the temperature sort of increases. So with time, so I'm going to send a lot of radiation onto the surface, and the surface heats up, and to begin with, the temperature is 20 degrees all the way. Then I start heating this up, and the temperature will start to become curves like this, and in the end, it'll just hit the surface temperature, and it'll start to ignite. So this is the temperature profile beneath the heated surface of a, we call it a semi-infinite solid. So it is finite, but it's thick enough to be considered to be fairly thick. So when we use the general heat conduction equation, this is classical physics, about 200 years old or something. Well, sort of. We get K rho C several places here. K is the thermal conductivity, density, rho, C is heat capacity. And the time for reaching T surface ignition is dependent on this and a number of other spatial variables. It's strongly dependent on the thermal inertia, K rho C. Let's have a look at a few materials. This is time, and this is a dimensionless temperature. It sort of goes from 0 to 1. We could just as well have from 0 to a couple of hundred, 300 or something. But it's just dimensionless, 0 to 1. So if we have polyurethane foam, fiber insulating board, oak, let's have a look at the polyurethane foam. It's very insulating. So we radiate to this or to the surface, and the surface heats up very quickly. None of the heat, actually, or very little heat goes into the material. So therefore, the surface heats very quickly, and then we come with a spark, and it'll ignite very quickly. Short time to ignition here. So this is the way that the surface heats up. But oak, which is much heavier, it will lead the heat in quite well, and it takes a longer time to reach the surface ignition temperature of about maybe 400 degrees. So it takes a much longer time to ignite oak. So sometimes we ask ourselves, what heat flux is required for this ignition to result? Is it 20 kilowatts per square meter? Is it 30? Is it 40? What's the lowest heat flux that I must have so that I can actually ignite this? This is often, we use this reasoning when we're doing fire investigations. We're checking, could this thing have ignited when I just had a fire here? Is it possible? And so we have to ask ourselves, what heat flux did it come from? How could this heat flux have been provided by this flame here? And so and so. How long would it have taken for this heat flux to work on that wall for that to ignite? And so and so. So we can answer a lot of questions like this if we know about ignition. And this is just based on sort of the fundamental laws of heat transfer, material properties and things like that. So now, once this is ignited, how quickly is it going to spread? What's the flame spread going to be? And the factors that influence ignitability also influence the rate of flame spread. We ignite something here, and we have a certain time to ignition. We'll have a flame. How quickly is this going to spread up? It is very much dependent on the time to ignition. The time to ignition is, or K rho C rather. So the same thing that governs ignition also governs to considerable extent the rate at which it's going to spread. But there are very many other factors that affect the flame spread rate, like the orientation, and a lot of other presence of edges, presence of some imposed heat flux, let's say a hot gas layer, or the direction of spread, the orientation of the surface. So in this case, we have ignited something at the top and it is spreading downwards. It's going to be very slow spread, very slow. Here, we've ignited something at the bottom and it's spreading upwards. It's about 100 times quicker to go up than to go down. So the orientation is, of course, absolute key here. So it's difficult to say things about flame spread, but we can classify solids by checking out time to ignition. How quickly does it ignite? And that's how we classify things, really. Now, this is just to show what the angle of, so if we increase, if we have something horizontal, the rate of flame spread is very low. As we increase the angle, we increase the rate of flame spread. So that was a very quick overview of solid ignition. So ignition and solids. So let's talk about smoldering combustion. So this was all piloted ignition. So we have a spark, or we have a flame, or we have some heated surface, or we have something that starts the gas phase combustion. Now we're going to have a look at smoldering. Okay, so that was all this was flaming combustion. So we have a flame. But now we're going to look at things where we don't have any flame. We just have smoldering. There isn't any flame, there's just smoke, smoldering combustion. It doesn't involve flame. It occurs only with char-forming materials because we need to conserve the heat. So we need insulation for the combustion to be able to continue to occur. The char is produced at a temperature of above about 250 degrees, And the char also oxidizes a little bit. And the heat released, it produces more char. Let's have a look at the cigarette. So this is tobacco, which is not burnt. This is ash. Somebody is sucking on the cigarette, trying to get the air to go this way, and the propagation of the combustion is this way. So we have glowing char at the front here. This is ash. It's relatively cold, actually, because it doesn't have very much heat capacity. But this is glowing char. This is what we call black char. This is where it's warmest, hottest. And here we have discoloration, and this is where it's actually burning. Typical materials that smolder: wood-based products, all kinds of cellulose, rayon, dusts and fibers of vegetable origin, rubber latex, some leathers, polyurethane foams, and so on and so on. This is a typical thing here. We put a little, we put a cigarette. There's a little cigarette here just at the corner. And after 7 minutes, it's actually burnt a bit. After 20 minutes, still there's no flame, still no flaming. It's just smoldering combustion. This is polyurethane foam. But it's the cardboard box that mostly sort of burns. After 1 hour, still no flaming, it's just smoldering. Smoldering is very different because it creates very, very little heat, but it can create a lot of smoke. And how does it initiate it? It's contact with smoldering source or contact with a hot surface. Exposure to radiant heat, or if we have spontaneous combustion. Spontaneous combustion is another lecture, very, very exciting. It's always very interesting when you suddenly get a fire in a number of very typical spontaneous combustion examples. Spontaneous combustion in hay, or if you have been putting oil on your veranda and you have a lot of cloths like this and you've been cleaning it up. You clean up the oil on the veranda with 5 or 6 sort of cloths. At the end of the day, you gather the cloths together, you put them in a bag because you're very tidy. You then leave the bag with the oil cloth. 6 hours later, when you're asleep in your summer house, then there has been a chemical composition and producing very, very little heat in the middle of these rags. Very little heat. But it's very well insulated. But it also has access to oxygen. So very little heat, so slowly and gradually it heats up, and after 6 hours, suddenly the heat just grows and grows and grows, and it spontaneously combusts, and it starts a fire. If you're lucky, it just dies down, and you're extremely surprised when you wake up the next morning. If you're not lucky, it's burnt down your house. So, but this is I love this subject. It's a lot of destruction and mayhem in this stuff. So at some point, this oil rag, it'll transit from being a sort of smoldering over to flame. And it's not really, we don't know very much about this mechanism, but it requires an increase in temperature and mass flow rate of the vapors, and suddenly you will actually get flame. But needs to be heated up quite a lot because the autoignition of many gases is up around maybe 500 degrees or something. So this is a smoldering fire. Here's a cigarette. And then we wait 20 minutes, 43 minutes, 53 minutes, and finally we get flaming. Finally there's flaming, 53.5 minutes, we finally get a flame. 1.5 minutes later, the whole chair. 3 minutes later, it's gone. It's just gone. Just before we go on to other things, I just want to mention there's a great difference. We started the lecture talking about pre-mixed gases. There's a huge difference between the energy released when you have a pre-mixed gas. Say you have 1 cubic meter of pre-mixed gas, and I put a spark in there. It's going to cause an explosion. It's going to be an enormous energy release rate, okay? But if I have a pre-mixed burning of a box or something, which is 1 cubic meter, it's much, much less energy released over a much, much longer time. So there's a great difference between diffusion flames and energy release rate and pre-mixed flame and energy release rate. Now, just a few words about enclosure fires. I'm going to go quickly over this now. So we can say also, you can read the book. It's actually called Enclosure Fire Dynamics. It's about room fires and how they happen. So I'm just going to go very quickly over this. We talk about pre-flashover fires and post-flashover fires. I'm going to say that the development of the rate of burning of a slab, this is a PMMA. If I burn it out in the open or in a huge big room, it's going to burn like this. The burning rate is going to be like this. It's going to burn evenly. But if I put it into a small room, then the radiation is going to go right down to the fuel, and it's going to increase the burning a lot. So it's actually going to triple the production of unburnt gases. So the enclosure does have a great impact on the fuel. It's just this is just to illustrate the key difference between a fire in the open, which we have been talking about until now, and when we take this material, liquid or solid, we put it into a room, then we can have a very different. And this is, we've talked about this earlier. It's about how we can go to flashover. How we talk about pre-flashover, and in this time we're trying to get people out, and then post-flashover. And in this period, we're trying to design the building so it doesn't collapse, things like that. So we've talked about this earlier. So, and mechanism for flashover, I've just actually, we went through this before lunch. So I'm not really going to talk about this very much. We're going to have hot flame spread over combustible surfaces, and rate of burning increases, and smoke accumulates, gets hotter, and then there's a feedback loop. It radiates down, therefore we get more burning, therefore we get hotter, therefore we get more radiation, and so and it feeds up like this, sort of cooks, and then boom, flashover. This is, here we have what's called the British call a front room fire. This is typical British furniture. As you see, it's a lovely, lovely little front room, it's called. And it's a pity they had to ruin this furniture for this experiment. But so it increases, you get a very, very hot layer, it cooks, and finally the whole thing ignites. And we can see that some of this table is actually evaporating gas. So unburnt gas is over here. Now we only need a little bit of spark so that this becomes a flame also. So we just need a little spark, and this will become a spark. This is very close to flashover. So everything is starting to burn here now. So it's just a question of seconds. Now, the side of the table leg suddenly ignites, and this suddenly ignites, everything ignites, and we get flashover. Like this. Now, smoldering fires, they produce cool smoke and sticky smoke and so, and the smoke can actually be flammable if we mix it with oxygen. Now, we've talked about backdraft earlier, so I'm going to go very quickly through this. This was the pre-flashover fires. We've actually talked about this earlier before lunch, so and we're getting thirsty anyway. So just a few words about the fully developed fire. That's when we're concerned about the structure. So we have the neutral plane, fire gases out, air coming in, and we did a lot of work in Sweden on how to calculate gas temperatures in fully developed fires, and it all depends on the opening factor, what the opening size is, because this is a ventilation control factor fire, and the main controlling factor is how much oxygen can get in here. And they came up with curves where you can actually calculate what the temperature is going to be like. I'm not going to go through this. It's basically they've incorporated this into the Eurocodes, and so this is the basis of fire-exposed structures. This research is the basis for how we design that in the Eurocodes. So we got different fire loads and different opening factors, and then we can actually tell you what the temperature in the room is going to be. So we can tell you what the temperature is maximum going to be. We have a look at this room here. We know roughly what the fire load is. We know if we open all the doors what the maximum amount of oxygen is going to be, and therefore we can identify a curve here, say the maximum temperature possible in this room, it can't get any higher, because we have these openings and because we have these combustible contents, the temperature is going to be like this, and then we design the load-bearing structure to withstand this. That's a way of doing things in the Eurocode. So we've been talking about materials and ignitability and flame spread. We've taken this material, we put it into a room. We talked very briefly about pre-flashover, post-flashover, and now we're going to take the fire out of the room. And what happens then is the smoke becomes much more important. And I think I just have 2 more slides. I'm going to show the smoke will actually. So we can have a fire far away from where people die. This, for example, was the Garley building in Hong Kong. 40 people up there died. And people down here got away. But the people died up there. The same thing happened at the very well-known MGM Grand Hotel fire. Pravin actually talked about this. Gandhi talked about this fire also in his talk. There was a fire in the started actually in the kitchen, and 80 hotel guests died. 18 of them were at the first floor where the fire was, but the majority was actually in the 4 or 5 top floors. So they died because of the smoke inhalation. So a little summary. Compartment boundaries strongly influence the fire behavior of the material. So we've been talking about ignition and how we classify gases, how we classify liquids, how we classify solids. But when we put these into a room, the geometry of the room is going to have a considerable effect. And the key factors are the amount of ventilation available and the area of combustible surface. And above the neutral plane, we will have overpressure forces flame and hot gases out through any opening, cold air in through the lower part. Temperatures above 1000 can be achieved in a fully developed ventilation-controlled fire. Severely underventilated fire, they will self-extinguish, but often, but sometimes they can actually create an enormous events, hazardous events like backdraft or something like that. So that was my presentation for today. Thank you.